Hello everyone, my name is Suyash Gupta, and today I'll be presenting our work ResilientDB, Global Scale Resilient Blockchain Fabric. This work I did along with Sajjad, Jelle, and Mo, and we did it at University of California, Davis. This work we'll be presenting for FAB 20, and it is also part of the proceedings of VLDB 2020. So, what is this work all about? This work focuses on blockchain and a key aspect of blockchain, that is consensus. Since the inception of Bitcoin, blockchain has found applications in different places like healthcare, energy, finance, cryptocurrency, and so on. Blockchain, the reason it is so famous is because it provides two key guarantees: decentralization and democracy. Basically, it supports existence of several replicas and gives each replica power to vote. In this manner, we can divide blockchains into two categories. It can be permissioned or permissionless. In this paper, our focus is on permission blockchain systems. We all know about permissionless blockchain systems like Bitcoin and Ethereum, and there are several of them. These blockchain systems allow anyone to participate, and identities of the replicas are unknown. The key issue with this blockchain system is that they face something called as forks in the blockchain. That is why a lot of people in the industry suggested moving towards permission blockchain system. In these permission blockchain systems, only a select group of replicas can participate, although some of them may not be trusted. Identities of each replica is known a priori. Now, for any blockchain application, irrespective of whether it is permission or permissionless, at the core of any of these blockchain applications is a Byzantine fault-tolerant consensus protocol. This protocol states that given a client request and a set of replicas, some of these replicas could even be malicious. The aim of this protocol is to ensure all the replicas order this client request in the same manner. Clearly, blockchain talks about decentralization, and that means not all the replicas will be in the same location. Replicas could be in faraway locations in different countries and in continents. So we thought of doing a simple experiment. We took 6 cities across the globe and thought of measuring the cost of ping and bandwidth. Clearly, if all the replicas are placed in the same location, then bandwidth available is very high and ping costs are very less. But if 2 replicas are placed in different locations, like say Belgium and Taiwan, then the ping cost will be very much and bandwidth is very less available. So what we realize is that how are existing consistent protocols doing in such scenarios? We took 5 state-of-the-art protocols and thought of checking their theoretical costs. And what we saw is that most of these existing protocols are centralized. They do not differ between local and global communication. And what is the impact is that if these protocols are centralized, then primary is the one person who's actually starting the whole consensus protocol, and all the replicas are basically sending messages to the primary. And there's no differentiation between local and global because all the replicas, whether they're in Belgium or Taiwan or Iowa, they still will be sending messages to each other. And that is how GeoBFT differs. In our vision of GeoBFT, we talk about clustering replicas. We talk about a system which is topology aware, which basically can differ between local and global communication, which can take advantage of inherent bandwidth. And if it knows that between 2 locations the bandwidth is less, send less communication between those locations. So GeoBFT is a topology aware protocol, and it basically clusters replica. And each cluster locally runs its own PBFT protocol. It replicates a request and then it creates a certificate. Once each cluster has created a certificate, then these clusters share the certificates among each other. And finally, once a cluster has all the certificates available, then they order every request deterministically, and then they execute these requests in the same order and send reply to the local clients. So how does GeoBFT works? Let us take example of two simple clusters, C1 and C2. Each cluster has its own local clients, it has its own replicas, and it has its own primary. The client will send its request to its own local primary. Each primary will run the local PBFT consensus protocol. The consensus, if you see here, is happening just within the cluster. The communication is happening just locally. Once the consensus is done, everyone creates a certificate and the clusters exchange the certificates. And then once everyone has got the certificate, now they execute the request deterministically and reply to their local clients. So that is how GeoBFT is able to save communication in comparison to other protocols. Now let us go over each stage of this in detail. The first stage is local replication. For local replication, right now we use PBFT because it is one of the most robust protocols. And PBFT is well known. PBFT allows in a system of n replicas up to f failures, where n and f are related by n is equal to 3f plus 1. In PBFT, safety is always guaranteed, while liveness is guaranteed only in the periods of partial synchrony. PBFT achieves consensus in 3 phases, and of these 3 phases, 2 require quadratic complexity. So how does PBFT work in case of GeoBFT? Well, the client sent its request to the primary assigns it a sequence number, and then he sends that request to all the other replicas. Note that some of the replicas could be even Byzantine. And then every replica agrees to support primary's request, and then it supports this by sending a prepare message. Once a replica gets 2F prepare messages, it has this information that at least majority of the non-faulty replicas are aware about this request, and then they send a commit message. And once a replica gets 2F plus 1 commit message, it has a further guarantee that at least a majority of non-faulty replicas, that is F plus 1, know about this request and they have prepared this request. So in case of GeoBFT, they create a commit certificate. In this certificate, the original request is there and 2F plus 1 equal to n minus f commit messages are there. Note the difference. Here, the replicas have not executed the request and they have not replied to the client yet. They've just created a certificate. The next phase is basically sharing this certificate. So here, we want the cost to be less because sharing is happening between 2 clusters and 2 clusters could be in different cities and continents. So we want only the primary of one cluster to send to only F plus 1 replicas in other cluster. And once the F plus 1 replicas of a cluster get, then they send that message to all the replicas in their cluster. So note that there is very less communication happening between the 2 clusters. And this F plus 1 messages are sufficient because the primary of cluster C1 is sending to at least F plus 1 people of C2. So even if both the primaries are faulty, then there's at least one good guy. So if PC1 does not send a message, then all the replicas C2 can actually determine that PC1 was bad and they can inform cluster C1 that, hey, replace your primary. Finally, the next step is basically to execute the request and order it. And for ordering and execution, we employ a simple criteria. Suppose there are 2 clusters, Ci and Cj. And if I is less than j, then requests of Ci are executed before Cj. We can apply different other techniques for ordering also. So we implemented GeoBFT on our ResilientDB blockchain fabric, and we make a claim that ResilientDB is quite fast and highly multi-threaded and deeply pipelined in comparison to existing blockchain fabrics. In ResilientDB, our intuition is basically to divide the task as much as possible and to employ as much parallelism as possible. As you can see, we have different types of threads. We have batching threads for creating batches, input-output threads for communication, worker threads take care of the messages, certification threads, execution threads. The whole architecture of ResilientDB is available to play with, and it is open sourced. Now, as we are talking about blockchain, then we need to actually maintain a ledger. And the key idea in ResilientDB is that for every ith request which is executed, we create an ith block. So in one round of GeoBFT, if you can see, there are three stages. There's local replication, there's intercluster sharing, and there's ordering. And this in this one round, if there are Z clusters, then Z requests are getting executed. For each of these Z requests, we create a different block. And to ensure immutability, in each block, we not only store the request, but also store the commit certificates, the exchange certificates. Finally, we thought of evaluating ResilientDB, and for that, we took 8 core servers and around 160,000 clients. We used YCSB as our workload and deployed replicas across 6 cities across the globe. For protocols where there's only one primary, which are centralized, we placed the primary at Oregon because Oregon provided the highest bandwidth. And in our first experiment, we thought of checking what is the impact of increasing the number of clusters. So we tested with 1 to 6 clusters, and every cluster, or in the whole experiment, we ensured that there are at least 60 replicas. Basically, if we are using 2 clusters, then each cluster had 30 replicas, and if we are using 6 clusters, then each cluster had 10 replicas. Clearly, GeoBFT scales. In fact, GeoBFT gains more throughput because it gets more parallelism as the cluster there, while other protocols are losing performance because lack of bandwidth. Our next experiment was to see, do these protocols benefit from batching requests? And clearly, if you can see here, GeoBFT benefits from batching, while most of the other protocols are facing limitation due to bandwidth. Hotstep does perform better than other protocols because it allows changing of primary, which helps it to balance the load, but still it is no match for GeoBFT. So to conclude, in this system, although we use PBFT for local replication, any other BFT protocol can be used. In fact, protocols like POE can be used. We asked clusters to share N-F commit messages, but modern cryptography can be employed. Threshold signatures can be used to create a small linear style message, the same manner which Hotstep does. It is possible a cluster may not have always a request and round, and it can just simply send a no-op message. How does GeoBFT benefit? GeoBFT benefits by reducing the global communication. Further, it allows this parallel local replication to happen that increases system throughput. GeoBFT is a topology-aware protocol. Thank you very much.